I'm just going to quickly go over how the relay computer works, or the one I'm designing. So it's going to have an 8-bit bus. It's got an 8-bit program counter, so an 8-bit address line. It will have a 4-bit opcode and 4-bit operand, which gives an overall 8-bit data bus, as I said before. We have these instructions. So I made a couple of mistakes, but I've corrected them. So the first one is our nope, so no operations. We have our add, so we add registers A and B, and then that is put back to A. Subtraction is a subtraction from A and B, put them back into A. We have an AND, a bitwise A and B. OR is a bitwise OR, using A and B. A NOT is a bitwise NOT on A. I'm not sure why I put B there. That should just be A. We have a load A, so we load using the memory address in C. So our C register will always contain the address that we're loading or storing or jumping from, or to, should I say. Then we have our load immediate B, so we load the operand, so the 4 bits in the instruction as well, but not the instruction, just the operand, and that gets put into B. MAC, we move A to C, deleting what's in A afterwards, and MCA is moving C to A, but we delete C after. And MAB, we're moving A to B, deleting A after. STA, we store data from A to memory, and then we use the address that's in C to find where to put it in memory. Then we have our unconditional jump, which will just jump unconditionally using the address in C. Then we have our conditional jump, which JZ is the jump of 0. So if you have the 0 flag set, it will jump using the memory address in C. And JC uses the carry flag instead of the 0 flag, but we still jump to the address in C. And then halt, that just stops the clock. And that's the overview of the system. So this is the architecture of the CPU I'm designing in relays. It will have an 8-bit bus and an 8-bit program counter. There will be a C register, an A register, the buffer for the A register, so we don't get an infinite loop. So A gets put into the buffer and then fed into these, and then we can reset A, put the ALU's input into A without affecting the input to the ALU. Then we've got B, which goes into ALU as well. That should also go to the bus. Just make that connection. We have our control board for the ALU. This will take a 4-bit or 3-bit input, which will then determine how the sequence happens in the ALU. We'll also have a control unit. I'm going to use dip switches with a decoder to easily be able to reprogram it. So you will take your instruction register, and your instruction comes in, which is a 4-bit, and this will be decoded into 32 lines, and the 32 lines will each have 2 lines per instruction, because there will be two clock pulses for the execute cycle and then 2 previous ones for fetch and then decode. So you will have 2 rows of dip switches. So on clock cycle 1, the first load of dip switches will activate the correct lines for all this, and then the second, because the number that goes in for decoding at the start will have 1 and 0. So 0 being the first clock pulse, and then the second clock pulse will be a 1 at the start, and that will then decode. So for each of your instructions you have 2 extra numbers for each decode, if that makes sense. And then those lines will then go out and control everything else. So I think that would be an easy way to reprogram it and program it without having to do loads and loads of relay logic, which that would take a lot of time. And whenever there's a problem, well, you've got to go in and change all that. So I think it'd be easier to just use dip switches. And I'll try the same for the ALU control board, as that will be less dip switches. So I can try that first, get all the problems solved with that, and then hopefully my control unit won't need too many revisions to work. The program counter will have an increment board, and that will go to the buffer board, which will then go back to the program counter, and that goes around in a circle, and that will allow you to always increment 1 and only start, or the end, I need to remember which one I want to do. We then increment the program counter by 1. You can also obviously put values into the program counter to jump. Conditional jumps rely on the flags, which I actually need to input into the control unit, because that will be required. The control unit can then make decisions based on the flags if it needs to jump. This is this board here. Arithmetic board is this one here. And then the logic board is this one here. And then our registers are these, which need to be reprinted, so this will not be the final one. And there's 1, 2, 3 registers plus program counter, which is a modified version of this board. And so is the buffer, just a modified version of this. There'll be 8 bits, as you can probably tell by the bus. All be made out of relays, apart from sadly the memory, which I will probably use Silicon RAM, just because 256 bytes of relays would be quite a lot of relays and would take up all the room, which would not be a good idea. So I have made register boards. The design is quite similar to that of Clickety Clack, because he showed an easy way of doing it with less relays, because my previous design had more relays than I needed. On this one we have our 8 bits. They are on each one of these relays. There is a loop that goes from the normally closed to its own power, and then that goes to this relay here. So basically what happens is when power comes in, it causes this relay to click on, which puts normally closed on, which puts power through there around, and it basically keeps itself on. And it doesn't matter if you take power off, it's on. The only way to turn this relay off now is to cut the power coming into this pin. And if you see, all of these pins are linked together and they come to this relay, which is the reset relay. If you put power into this one, it goes from normally closed to normally open, and the power won't come through here anymore. So it's basically an inverter. Cuts the power off, and that cuts the power to all these. So if there's a bit held in any of these, it will reset it. These relays down here are basically gatekeepers. It stops power on these being put out onto the bus unless the set is enabled, which is one of these ones over here, that one. So when set is enabled, all of these can then pass through and either set these or allow the power out to the bus for reading it. And then you have a reset, which activates this one, which cuts the power to all these. Then you have this one over here. This pulls off the power in the relays, so you can read the bits without having to set. And this will go off to the ALU. And there will be 3 of these boards. So your C register, A and B registers, and then the buffer board for the ALU, the program counter and its buffer, and also the instruction register will be basically the same as this, just slightly different placements. So this is the logic board. We have our 2 inputs from A and B. B passes through the control unit of the ALU, because for NOTs it has to be off, because we only do it on A. By default, without any inputs or without changing these, it's always doing an AND operation, a bitwise AND on the 2 inputs. ANDs basically work by you put the power through to this one, which turns this one, and this one, which changes through and puts out. An OR is using these 2 relays as well, while a NOT uses this relay here, and it basically is on the always closed. If you power it up, well, it goes to always open, or normally open, should I say, and that breaks the power, which turns off the output. With a NOT though, it has to only be the A, because these ones are not hooked up to anything, so when you put values in here it just does weird stuff, so you just don't do that. There are diodes here because they all connect up, and without that it causes back feeding and stuff, because it go back round here and through this line, which then feeds to all the other ones, and they're all open, so it feeds back round. Yeah, it's not a good idea, so diodes are needed. On the current version I've made, or I've got it printed, I forgot to put these in, so I have to get that reprinted. And then these are always the diodes, which are always needed. That's basically how this board works. So this is the arithmetic board for my relay computer. Basically how this one works is it can do add or subtract. We have our input A, input B. We have these ones, don't worry, these ones. So logic, set and reset. But for my old design, they just pass straight through, which you don't need to know about. But A and B are used in the arithmetic maths. We have our subtraction line. So when this is activated, these relays will basically compute the 2's complement of input B, and then all it basically does is adds the 2's complement to A to subtract it. And here are your adders. It's a carry over a ripple carry adder, so nothing too fancy. And then yeah, here or 1's complement, and then to make 2's complement you just turn the carry bit on into the adder, which basically adds 1. And that's how this system works. So this is what ties together the arithmetic and the logic units, and it also takes care of carry flag and 0 flag. So on this board you have your input from the arithmetic board and the one from the logic board. By default, this will always output arithmetic when it's enabled, which will be this one. When this pin is on, it enables the output, and that basically works by these relays here have it going into terminal here, and when you enable it, it puts power to all these relays, and it switches to the normally closed, and the normally open is attached to these, but it first goes through the 0 check. Now the 0 check works by having a chain. Basically power comes in at the bottom, works its way all the way up, and comes back out. If, as you see, they're always to the normally closed, so if there's no data, then all of these relays will be off, and the power will just go from that pin to the normally closed and ripple through. But if a single one of them is on, then it will break the chain, and you will have no power coming through. And then 0 flag is here. Gets outputted next to the bus, and the carry flag comes in from the carry register, and you set the flags using the set and reset. Now you must always reset the before you can set it, or otherwise it will basically do an and that's how this one works. Or you have your LEDs here to show you the current status of the flags, and that's everything. So this is the ALU control unit. This will control everything in the ALU based on the input word that comes in here, or the control input. This is a 3-bit number which tells it if it's an add, subtract, an and, an or a not. You have an extra bit which is which clock pulse we're on. If we're on the first or second part of the execution cycle, that goes at the beginning of this decoder. Basically this just decodes a 4-bit value into 10 lines, and these 10 lines will then have dip switches, which you can then reprogram to anything you want. So you can quickly change the microcode for the ALU by just changing the dip switches without having to continuously reprint boards, which I think is a much better way of doing it. But it does require a lot of diodes because you need to stop, because the switches, if you have them all just connected up to here, it will go around and it will short itself out to all the other ones. So you need all these diodes along here, so the power can only flow that way and not back through the switches, and then shorting, not a good thing. This bit over here is for cutting input B, because input B has to be stopped when doing a not operation, or otherwise it goes wrong because it doesn't like it if there's 2 inputs in the logic board under a not. So this just gets cut by these, and this basically activates the cut only when a not operation. As you can see, if I highlight that, should be able to see this pin here, these ones here light up, which shows you that that's connected up to it, and that activates this relay which cuts the power from the normally closed to normally open, and that's the power that powers these relays. So these turn off, and well, the power can no longer go to the output. On the side we have all the LEDs, which just shows you which step and which instruction it's currently doing. So we have our add 0 and 1, so these are the 2 steps of the execution cycle. For add and sub 0 and 1, and 0 and 1, or 0 and 1, not 0 and 1. You just change these dip switches to whichever one you want. That then goes out onto this, and this will basically go out to all of the boards in the ALU and control them. So that's everything on this board. So here are 2 of the boards from the ALU of my relay computer. So this one is the logic board. Takes 2 inputs and a single output. You have and, or, and not. By default it's always putting out an and, but you can change it to an or a not. This is the adder board. It also is a subtractor at the same time. It's 8 bits, so you have an 8-bit input here, A and B. You have a subtract line. Don't worry about the other ones, those were to go through to the next board after this one, which is this board. will be this way around. You have your two inputs, and you can select which of the two you want. So if you want a logic, it's there. You would say logic. You would put a high pin in that, and it would switch to the logic. By default, it's always going to output the arithmetic boards to the bus, which will be connected to here. You have your select, your enable, so only when this is enabled will it actually output to the bus. You also have your carry in, which will set. So you have your set and reset pins for 2 registers or 1-bit registers, which are your carry and 0 flag. So if there's a carry and you do the set, you'll get a flag which is going to be carried out on these 2 pins. And in here you have basically a chain of relays. If a single one of the inputs is on, it breaks a chain and the 0 flag cannot be turned on. But if all of the inputs are 0, then the chain of relays is not broken and it will output a 1, which will then be latched if you do the set. So this board basically puts together everything from the other 2. Now I have the logic board, which I will test. Sadly on this design I have disconnected the wrong way around, which I will improve on the next version. Right, so by default it will always AND, so putting a 1 on this side give us nothing, but as soon as we put that 1 on the other side, it should AND that and give us a 1 output. Yep. You can try the same for the next bit. Yeah, that seems to work fine, and then we can try that for the 3rd bit, which works as well. We can now do an OR by selecting OR, which is just there. So we have an OR and a NOT select. Let's do OR to start with, and if I remove everything from there, we get nothing. If we do any of these, you get a 1 for any of them. There we are, yeah. And the same on the other pin. Yeah, that all works perfectly good. Now does both of them together work? Yeah. Let's try bit 2. Yeah, that works good. Let's try NOT operation, which only works on input A. So I need the system to cut out input B because it causes problems. So they're all on because it's the inverse. If I do the inverse of 1, if I put a power onto here, it should give us 0 for the first bit. It does. And the second bit. Yeah. And the 3rd bit. And that works perfectly fine. But if I do it on the other one, it just causes mayhem. So that will need to be cut using a Mux or something. So this board works perfectly fine. Except there is one problem with the OR. I don't think it'll be a problem though, because the inputs are put into this board well before we need the outputs out. And when we first do an OR, all the lights seem to turn on for a split second, which I found the problem. We need diodes to prevent backfeeding in one part of the circuit, which I will do for the next version, but for now I think this will be fine. So this is the adder board, which I'll be testing now. So if I put a 1 into input A, we should see a 1 on the LED, which is here. And we see that. And we should get the same on input B. Yeah. If I put a 1 on input A and a 1 on input B, we should get 2. Which we do get. And then 1 plus 2 should give us 3. So if I put a... yeah, there we are, get 3. And if I do a 4, 4 plus 1 is indeed 5. And if I put a 2 on input A, oh, what happened there? light's gone out. No, it's just a bad connection there. Right. So we get that. So if I then put 2, I input A, and then get 6. So that's all working. I would like to test all the other ones, but I need to get more LEDs and a bit more wire for that. We can now do the next one, which will be subtracting. So we take a positive lead, we attach that to the subtracting bit, which is down here. I don't know if you can see that, but one of these pins, you just put power to it, it changes it over to subtracting mode. So B is our B will be 2's complement, so 1, that's 2's complement of 1, 2's complement of 2, 3, or 4 shall I say. Right, so we can now try some subtracting. So if we put a 1 in input A, it'll give us a normal 1. And if we put a 1 in input B, we should get 0, which we get. Now we put a 2 in input A, and we subtract 1 from that, we should get 1, which we do get. And subtracting 2 should give us 0. Yeah. Input 3 and input A, which is actually 4 I mean. If I subtract that by 1, I get 3. Subtract that by 2, I should get 2. Which I get. Subtract that by 4, I should get 0. Yeah. I can also try subtracting that by 3, see if we get 1. Just bridging pins 1 and 2. Yeah, and we get 1. So that all seems to work perfectly fine. This is the last board which I've actually populated, which is one of the registers. Now I do know that number 6 does not work on this one, as I made a mistake and, well, they all go to ground, as I accidentally put one of the traces to ground, and well, I auto-traced it and, well, yeah, put it all to ground. So this board is unsavourable, but still test to make sure the rest works. So put power in. You can put ground. Then we shouldn't have any, should get no registers clicking in unless the set is on, which we do get, which is good. We don't need these LEDs as we have our indicators here. Now if I enable this, so if I put a 1 in and then enable, hang on, that's the bigger bit which we haven't populated. So if I enable that in, should get this light turning on. Should get that light turning on. Oh no, it is this one. There we are, so we get it in, and if we remove it, it stays, which is the point of the register. And if I reset, that will get rid of that, which works perfectly. Number 2 works as well, and then removing that keeps it there, and then resetting gets rid of it. But number 3 is where I was saying the problem is. If I connect that up, that power supply won't be happy with that. Enable it, nothing happens because, yeah, it's not happy with that. Number 4 should work. It does. Can reset that. Number 5 works. That can be reset as well. And number 6 should work as well, which it does. That can be reset.